In lecture, we saw that we can use the Euler-Lagrange equations to deduce the general form of a minimum velocity trajectory for a first-order system. In this segment, we'll go through the details of that calculation. In lecture, we considered problems where we had to find the function x star of t that minimizes the integral of a cost function L over t. When looking for the minimum velocity trajectory, this cost function is x dot squared. The Euler-Lagrange equation gives the necessary condition that must be satisfied by the optimal function x of t. Let's evaluate the Euler-Lagrange equation for the problem of finding the minimum velocity trajectory. Again, the cost function for this problem is L equals x dot squared. First, let's individually find each term in the Euler-Lagrange equation. Here, it is important to take care to differentiate with respect to the proper variable. The partial derivative of L with respect to x is 0. This is because the term x does not appear in L. The partial derivative of L with respect to x dot is 2x dot. Note that in this step, we are not yet differentiating with respect to time. Finally, we can evaluate the time derivative of partial L partial x dot. Using the value of partial L partial x dot found in the last step, we see that we need to take the time derivative of 2x dot, which is 2x double dot. Now, we can substitute all these terms into the Euler-Lagrange equation. The equation becomes 2x double dot equals 0, which is equivalent to simply x double dot equals 0. This is the condition we saw in lecture for a minimum velocity trajectory. We can integrate this condition once with respect to t to get the velocity. Here, c1 is an arbitrary constant. We can integrate the velocity to get the position function for the minimum velocity trajectory. Here, c0 is another arbitrary constant. In lecture, we discussed how c0 and c1 can be found from the problem's boundary conditions.